Remember the days of the flip phone? Trying to get the internet on one of those was, well, a huge challenge. Today, we're going to explore the ingenious technology that actually made it happen, WAP, the protocol that somehow squeezed the entire web onto those tiny mobile screens.
And seriously, have you ever really stopped to think about that? We totally take for granted that we can browse anything from anywhere on the supercomputers in our pockets. But back then, connecting a phone to the web was a monumental task. So how on earth did they pull it off?
The answer was a really clever piece of engineering called WAP, which stands for the Wireless Application Protocol. It wasn't just a quick fix, it was built from the ground up, specifically to solve the unique problems of that early mobile world.
Okay, let's really paint a picture of this hostile environment they were working in. We're talking about internet connections crawling along at 9.6 kilobits per second. That's slower than old-school dial-up. The processors in these phones were so weak, a modern smart toaster has more power. Throw in tiny black and white screens and almost no memory, and you can see why loading a normal web page was just impossible.
So, to deal with all that, engineers couldn't just tweak the existing internet. Nope, they had to create a whole new blueprint for mobile data. And that blueprint is what we call the WAP protocol stack. Let's break down how it worked. So here's a look at the entire structure. Just like the internet we use today, WAP is built in layers. I think the best way to imagine it is like a stack of specialists, where each layer has one very specific job, and they all work together to get that tiny web page onto your phone. So let's start peeling back these layers. Here's a quick roadmap of our journey down through the stack. We're going to start at the very top with the application environment and go all the way down to the physical networks. You can see each layer has a very clear purpose, from handling the apps you see, to managing security, to making the data transfers happen. So let's start at the top, with the layers that are closest to what you, the user, would have actually seen and interacted with. We're talking about the application and session layers.
Right at the very top of the stack, we have the Wireless Application Environment, or WAE. This is basically where all the apps and services lived.
Now, the secret sauce in the WAIA was a special language called WML, or Wireless Markup Language. Think of it as HTML's super lightweight cousin. It was designed to create web pages that were incredibly simple, perfect for those slow phones and tiny screens. This also gave developers one standard way to build apps that could run on all kinds of different phones.
Okay, moving one layer down, we find the Wireless Session Protocol, or WSP. And like the name says, this layer's job is all about managing the session, or the entire conversation between your phone and the server.
What's so clever about WSP is that it was basically a rugged, stripped-down version of the web's HTTP. It was built for unreliable wireless connections. So if your signal's dropped, which it did all the time, WSP could just pause the connection and pick it right back up when the signal returned. You didn't have to start the whole thing over. That was absolutely essential back then. Okay, now we're moving deeper, down into the engine room of the WAP stack. These are the layers that handle the real nuts and bolts of moving data around reliably and securely. Welcome to Layer 4, the Wireless Transaction Protocol, or WTP. This layer is just a fantastic example of how WAP was optimized for the wireless world. You see, the regular internet uses a protocol called TCP, which is great, but it's heavy. It's like making a formal phone call. You have to establish the connection, talk, and then hang up. There's a lot of overhead. WTP, on the other hand, is way more like sending a text message. It just sends a request and gets a response. That's it. This transaction-oriented way of doing things was way more efficient for the small, quick bursts of data you needed on a flip phone.
Next up, let's talk security. With any kind of online communication, you have to know your data is safe. In the WAP stack, that critical job fell to Layer 3, the Wireless Transport Layer Security Protocol, or WTLS.
WTLS was adapted from the Internet's standard security protocol, TLS. It was tweaked for mobile, but it still provided the three crucial pillars of security. First, data integrity, to make sure no one tampered with the message. Second, confidentiality, which used encryption to keep it private. And finally, authentication, which just made sure you were talking to who you thought you were talking to. All right, let's get down to the very foundation of the stack. These are the lowest layers, the place where the digital world of WAP meets the actual physical hardware of the mobile network.
At Layer 2, we have the Wireless Datagram Protocol, or WDP. And this layer is kind of the unsung hero of WAP's versatility.
Think of WDP as a universal translator. It sat on top of the physical network and presented a single, consistent interface to all the layers above it. What that meant was the WAP browser didn't need to know or care if it was running on a GSM network or a CDMA network. WDP just handled all the differences and made it work seamlessly.
And finally, we arrive at the very bottom. Layer 1, the bears. Now, this isn't really a protocol, but the physical networks themselves.
Because of that really clever WDP layer we just talked about, WAP could run on pretty much any mobile network technology that existed at the time. So whether it was GSM, which was popular in Europe, or CDMA in the US, or other systems, WAP was designed to be adaptable and just work across the board.
So if there's one thing to take away, it's this. Every single layer of the WAP stack that we've just looked at was purpose-built to solve a problem. It was a complete top-to-bottom reimagining of how to deliver data in a world with some pretty severe technical limitations.
And that leaves us with a fascinating thought, right? While WAP itself is history, the principles behind it, designing lean, super efficient protocols for low-power, low-bandwidth devices, are actually more relevant than ever in our modern world of IoT and smart devices. It really makes you think, what lessons from tech's past can we apply to build the future?